So this is a video showing my AP class's finished product of their bonding molecules, their bonded orbitals of several different types of molecules. This, if you haven't already guessed, with its sp3 hybridized structure, with the s orbitals overlapping the sp3 in an angular or bent shape, is water. Water has that nice bent shape with the two lone pairs, as you have seen two-dimensionally, but it's nice to show it how it really would look three-dimensionally by the VS-EPR bonding, or actually repulsions of the electrons in the sp3 orbital. So this is the hybridized orbital. One s and three p's came together to make four equally shaped balloons or orbitals, and two have lone pairs. So this would be a lone pair here, and you'd have another with a lone pair up here. And those two lone pairs keep the basic shape of a tetrahedral in terms of electron domain geometry, but the molecular geometry is where the atoms are. So right in the middle would be oxygen, and here would be the hydrogens with their s electrons overlapping sigma bonding the sp3s, and that's where you get the 109.5. Now for water, because of the two lone pairs, they actually bend this downward into about a 104 bond angle, but a 109.5 is good enough for now what we're doing. So that is water in all its glory, and it gives you a good three-dimensional feeling for how water looks. And sometimes you don't really see the two lone pairs drawn, and some people two-dimensionally you put them this way, when in fact, you would actually have it shown this way. So yeah, that's how water looks. Of course, the two lone pairs up top we don't consider in terms of the molecular geometry, but because of the two lone pairs, they bend down those two other sp3 bonded sigma bonds here into a very asymmetrical shape, and you would have the more electronegative atom pulling electrons up, making a polar molecule. Negative part on this side, positive part where the H is, and if you're doing dipole moments, you'd have the positive part of the polar bond going up, and you'd have two dipole moments. The overall dipole moment goes up, and there's your polar molecule. And because of that bent shape, water is polar. It has a positive and negative end to it. And there it is. So we move on down to acetylene. Now acetylene has a three-dimensional structure. If you do Lewis dot diagrams, we would get a linear molecule, as we can see somewhat here. This linear molecule. Now this linear molecule basically tells us, with no lone pairs up top, that it's sp hybridized between the carbons. So this is an sp orbital, so is this. This is an sp orbital overlapping directly with another sp orbital, and that's your sigma bond. And there's another sp orbital, as I'm into the light here. And what you have to the left and to the right of your sigma bonds is unhybridized p's going out. This is let's call this py up and down, and then you got pz coming at you and behind you. And if you notice, we got some pi bonds working. Not only do we have the sigma bond between the unhybridized between the hybridized sps that make it linear. If it's sp and s and p came together, and knowing that there's three p orbitals, that means two are left unhybridized. And those are the ones that are allowed for pi bonding. And you can see the pi bonding in this case is front and back. It's my front, and if I turn it over here, whoa, we got the back, And then we also have, on the other side of our molecule, C2H2, which is otherwise called ethine, we also have top and bottom pi bonding. So you can see the top py orbital, we'll call it, is also pi bonding, there as well. So the triple bond is two pi bonds and one sigma. And of course, we have the sigma bond with the hydrogen at the end. So there's our sp hybridized molecule that is linear. Sp always denotes linearity. And the two extra bonds are the two unhybridized p's, front and back, top and bottom, creating that extra second and third bond there. So very non-polar molecule, because the dipole moments cancel out, because it's very symmetrical. Also, you could say it's non-polar because the hydrogen has about the same electronegativity as the carbon. Okay, it's about a difference of 0.4 or less, so it's considered to be a nonpolar bond as well, depending on what curriculum we use. And then my favorite of all is CO2. CO2, okay, has this structure, and very symmetrical structure too. Notice there's no lone pairs bonding this downwards, so it's also linear, so it screams to us sp hybridization as well. And there it is. There's our sp orbital. Here's a carbon, and there's its two sp orbitals. Here's another carbon, and it's, I'm sorry, we have one carbon in the middle, sorry, and its sp orbitals on both sides are white. And on the end we have the unhybridized oxygen, which is overlapping one of its p orbitals, unhybridized p's, with the sp of the carbon. And then we have another unhybridized p orbital with overlapping directly sigma bonds with the hybridized sp. So the sps are overlapping unhybridized p's and causing those two sigma bonds. Now, because it's sp, just like we did with acetylene, the first bond is the sigma bonds. Okay, the first bond is the direct overlap between the hybrid orbital, sp orbital, and the unhybridized p. And over here, the same idea. So we get those two, okay, one there and one there is your first bond. Your second bond has to be from a pi bond because, well, the geometry states that you really can't have an overlap in two directions. So if you're overlapping here, there's no way to overlap again. So we have that pi bond going on. Bottom, in this case, bottom and top, okay, there's a pi bond going bottom and top, and then the other side, it has to be front and back. And the reason why the middle one can do that is because, well, the carbon, because it's sp, has two what? Unhybridized p's that can go what? Pi bond. So front and back, in this case, to this unhybridized p, and top and bottom. It's like a chain link fence, so to speak. But this molecule is nonpolar because its polar bonds are canceled out by two dipole moments that go outward, and they're the same arrow. So because of the symmetry, this molecule is clearly a nonpolar molecule, and therefore it doesn't attract each other very strongly. That's why CO2 with a molecular mass of 44 grams per mole exists as a gas at sp, whereas our water molecule, right, 18 grams per mole, which is more than twice that of CO2, less than twice, actually, more than twice in terms of the number. So it's more than half as heavy, and it exists as a gas. I mean, as a liquid. Why does this at STP, water, exist as a liquid when it's a lot less heavier? Well, the reason is because of its bent shape, it is more polar. So water exists as a liquid state because of the positive and negative nature. Here's the positive part of the molecule. Here is the negative part. And because of that, water attracts each other very strongly, and water resists evaporation. And water, of course, is very unique that way, but water exists as a liquid because of its polar nature. And because of its polar nature, the positive end here, negative end up here,